All right, sweet. Hey, Jacques is here. Yeah, awesome. I will share my screen. Sorry for the short notice, and thank you folks so much for having me. I assume everybody can see my screen and hear me.
Yep.
Okay, so I'll be quick with this. My day job is at a company called Hasura. It's sort of like an open source tool that basically takes database connections and auto-generates a GraphQL CRUD and real-time subscription API on top of them and does a bunch of other stuff too, but that's not important. I'm just sharing this so that you folks kind of have the context of where I come from. But the idea is that you're able to query in GraphQL and say that this album's table was in Postgres. You can make virtual joins. Say we have a tracks table in SQL Server, and you could sort of do a distributed queries across multiple data sources and also REST and GraphQL APIs. Same like mutations as well. So the way that GraphQL works, if you're not familiar with it, is that you sort of query for data in the shape that you want. So if I just hide this for now, we can basically say, I want all the users where yada, 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 and on their fields, I want these columns from the database. It's super great for developer productivity. The APIs are strongly documented because every operation has to have a type, and tables and whatnot have to have types. And the way that Hasura works, if you press analyze, you can see that it's really just generating a bunch of SQL, and we'll do like cross-DB joins. So Hasura is really cool, but it is built, the query processor is built in Haskell. And while it's fast, we don't have that many data sources that we support. So if you see down here, we really only support at the moment like Postgres, SQL Server, Bit, and BigQuery. So I thought it could be a really fun project if I tried to build a sort of a clone of Hasura and GraphQL. So basically the way that it works is that you come in here, you click manage your databases, you can connect the database, whatever, and then you'll have these tables here that have an API generated for them. So something that I've been working on is like a rough proof of concept of doing this with Calcite on the JVM. So this is essentially the project. So the idea is that as a user, I would like to be able to access and modify, so not just query data stored anywhere, as long as it has a well-defined structure. So that could be a relational DB, a non-relational DB. It could be data stored on disk, CSV, JSON, Parquet. It could be in-memory data. And I would like to be able to query data from multiple databases in a single query. So distributed or federated querying. And I would also like to be able to join data that are stored in disparate data sources with sort of virtual relationships. And what's also imperative is performance. So it's super critical that it has low latency and that the P90 for queries is competitive with a handwritten server implementation. And also federated queries ideally should complete quickly enough that you can use them in day-to-day user-facing apps. And as an engineer, I would really like if I could have sort of an industrial grade query planner and optimizer that backs the execution. I want something that's extensible. So if a data source isn't supported or I want to connect it to something that I own, any engineer should be able to write a plugin or whatever you want to call it and sort of add new data sources. So a good example of that is like Airtable. So if I want to be able to expose Airtable's REST API as a GraphQL or SQL queryable source, I should be able to write the translation layer from what Calcite calls a rel node to Airtable's query criteria and be able to do that through HTTP so that you don't need a reliance on the JVM. This is basically a really shitty version of a project that Jacques is working on called Substrate, very similar goals. And I would really want to work with a widely used and mature set of tools. Haskell is cool, but there aren't that many Haskell engineers and it doesn't have the best ecosystem. And standardization. It's best if things work on standards. So JDBC, Substrate has a specification. Calcite is very common. People have spent a lot of time thinking about this, and I really don't know that much. So the way that this works is I stole these images from Stamatis' presentation, by the way. It's really fantastic. You have a query processor, and the architecture is generally the same. You have a parser parsing some sort of representation, and you have a plan builder. And that's going to build your operator tree, goes to the optimizer, it gets executed. And then over here, you have a catalog reader that's providing schemas. So that's the source of your data. With Calcite, typically what you have is the SQL parser and the SQL to rel converter. So if we look at this, we can say, hey, what if I just kind of took this whole box here and I threw that away and I wrote a GraphQL query parser and GQL to rel converter instead. And then we can just auto-generate the GQL schema from Calcite schema and catalog readers. So essentially what it does is the exact same thing as the SQL parser. This project consumes GraphQL queries and it converts them into an internal form, and we can use that to generate rel nodes. So the actual architecture of this, and this image is small, so I'm going to open it in a bigger one so people can see, is that you start with a GraphQL query like we have on the left in part 1. The query is parsed, and we get part 2, which is the GraphQL query AST, and this is a big class object on the JVM. And then I have an internal IR that I'm not particularly attached to, but it just makes things easier, could be inefficient, where I represent this query as a table selection that has conditions and projections and joins. And then finally, what happens is that I sort of just traverse that and I convert this intermediate representation AST into a rel node. And then you can, of course, do all the things that you can do with rel nodes with that. So if this sounds cool, you might wonder, like, what's the status? Something I should mention is that this only works because we restrict the domain of GraphQL to things that are possible with SQL operations. As of today, here's the status, and I'll show a quick demo after this. But I can convert a Calcite schema into a GraphQL schema. I can parse the GraphQL query AST into the right rel nodes. Mostly, I have where, limit, and offset done. I don't really understand the distinct and group by APIs as well. Those are the sort builder APIs. You can execute the rel node against the data source and return the right results. I'm working on writing the generation of what GraphQL calls resolvers, which are basically data fetching functions, and that will make the schema interpretable. Right now, I'm just running it by hand. Queries are supported. I'm working on building out support for mutations, which is data changes. Calcite has streams and streaming queries, which I believe I can use for real-time subscriptions in GraphQL. And that's something that I plan to work on after queries and mutations are finished. The things that I'm working on in the immediate future are join, writing the join builders for nested queries. So let me go back to the query here. You can see that I have this user, and I'm selecting the ID and the email on user, and I'm also selecting to-dos. That is going to be the join query, and I've only been able to write the code for the top level sort of column scalars. What I need to do there, I think, is I need to use these rel referential constraint informations from the schemas. And then I need to build on top of that and somehow implement virtual or cross data source rel referential constraints. I'm not certain if that's right or if it'll work, but from reading the code, I think that's probably what I need to do. And then I've also designed a system for dynamic registration of more schemas when the app is running, because like you saw, you can add more databases while the app is live. And then this is just in the future, that extensibility part. So how do I allow users to also implement their own backends and plug into this metadata system? So there's a couple of challenges that I've hit. So I actually don't have any formal education. I dropped out of high school and I never went to college. So I have a poor understanding of backing theory behind relational algebra and like general RDBMS stuff. I'm new to Calcite. It's a very large code base, and there's not that many resources, especially because what resources there are generally focus on parsing SQL or working with SQL, which is, I guess, kind of that makes sense. That's what most people want to do. But there wasn't really an easy guide on how to work with custom like AST or different front ends and lowering that to rel node expressions. And the last one is that performance is critical. This whole project is useless if it's not performant enough to be utilized in an actual production backend. And I'm continually checking to see if Calcite will be fast enough while I'm writing this and how I can make implementation code faster. JMH benchmarks currently show an end-to-end query. So consuming a GraphQL query, parsing it into a rel node, and then executing it against an H2 end memory JDBC backend. That's averaging about 2 milliseconds with no joins. And I think that's solid. So it looks okay there. We'll see kind of what is in the future. And with that, I will say thank you, and I'll show a demo. So I want to say that it's taken a lot of help from others just to get to where I'm at, which isn't very far. And if any of you find this project interesting or feel like being nice, I would appreciate any help. Could be code reviews, could be, hey, don't do this, that's a really stupid way of doing it, or the best practice is whatever. Or I wouldn't build it this way because you'll run into problems. All of that info is super appreciated. So if you want to see this thing working and you're bored of me talking, what I have here is basically the JDBC Scott test database. And I'm going to make a query on the employee table and select this stuff. And we'll just ignore all this down there because that's the implementation. But if I click run, you'll see this run. And we can kind of check out what happens here. So the first thing that happens is you'll see that it converts the tables in that JDBC schema to types. So we have our emp type here with the rows. It generates queries for them. So here's our emp query. These are all Boolean expressions that allow you to do the queries. And then what happens is it gets converted to this internal AST form. So this is the parse GraphQL query represented as like my really shitty IR. And then represented as a SQL query, you can see it comes out as this. So there's even some good optimization going on in there where it's converting the ors to in clauses. Then we see the logical and the plan steps. And finally, when we execute it, you can see right here that we have two results, Jones and Blake, both managers. If I were to take out the department number with 20 and I run it again, then this guy Jones should be gone. Yeah, no more Jones. Now we get somebody named Turner. But yeah, so there you go. That's pretty much what I've been working on and the state of things. I'm trying to build a schema manager that holds all the database connections and generates like the foreign key relationships. I think maybe I can do it with some sort of combination of the physical foreign key map and a virtual foreign key map that I then combine. But yeah, that's pretty much it. Thank you for letting me present.
Hey, Gavin. I found the presentation very, very interesting. Also, I'm not very familiar with GraphQL. I'm a bit familiar with general graph query languages. And yeah, I find the work so far impressive, let's say. So yeah, let's see if people have questions. I don't see something popping up in the chat. But yeah, let's focus on the questions about Gavin at first, and then we can also go back to join reordering or Calcite enclosure or anything else. Yeah, in the meantime, since I don't see any questions, yeah, I would like to say that a lot of things that I saw in the demo and the presentation seems like that it would be a great contribution to Calcite, like the GraphQL parser or GraphQL to rel node, also very interesting to have in Calcite. I guess it will help many, many people. And I guess other parts as well when you get back to the execution, to the actual execution of things. I think all these are definitely fit the Calcite adapters that we have, and it could be a new adapter or something similar. A comment I didn't completely get the point that you meant that you would like to have the same performance with a handwritten implementation. At what level? You meant that, Gavin?
Yeah, so part of the reason why Hasura is, I guess, attractive is because generally with no-code tools and ORMs, they generate inefficient queries. You have like n+1 queries and their performance isn't optimal. So I don't think this will be a problem because Calcite does query optimization, but the queries that it generates in the execution ideally should happen fast enough for people to be able to use them in their applications and them to be competitive with, let's say, like a controller method that runs a query that they had written themselves. So if I do like a nested select, if I want to join filter users and join on X and join on Y, running that on the GraphQL API shouldn't be slow. It should be about as fast as if you had written the business logic yourself in a controller. Hopefully.
So yeah, Gavin and I were talking about this at one point, and I think that the comment that and some of that may have come, the concern may have come from something I said, which is that I don't think that most people are running Calcite query planning tens of thousands of times a second. So like what more like an OLTP engine would do. And so it may be that you find that there's certain parts of Calcite that just insert 5 or 10 milliseconds of latency, which may not be acceptable in an operational workload.
Yeah, that would definitely destroy a lot of the benefits. But well, fingers crossed, and we'll see.
Okay, yeah, I think I got a bit misunderstood the goal, because I thought that you would like I have the GraphQL and I want to get the best physical plan. Like if somebody was writing the physical plan, let's say, or the operators, it was putting the operators manually like that, like in a particular way, you would get the same performance, which is, yeah, I guess very difficult to achieve. I mean, there is no, even the best query optimizers cannot do that. So
yeah, no, I think it was more about just the general concern around the insertion of just any latency in an operational query.
yeah.
I had a similar idea to see if GraphQL could be implemented in over Calcite. So congrats on doing the work for that. I think it's going to be a very useful tool if you manage to implement it and have it working. I did work on implementing a GraphQL API, and I kind of got to see the issues there with the n+1 queries. And I'm curious if you have thought about, because joins will be an issue. Have you thought about the n+1 problem and how? Because I think eventually you'll have to, if a GraphQL query is pretty deep, you'll have to run multiple. You have to split the query and run multiple queries at once, or I don't know if this is.
That's a great question, and I'm kind of interested in that too. So really all that I'm doing is like taking the GraphQL and using a rel builder to say like, this is the equivalent expression. And then I'm just kind of crossing my fingers and hoping that what Calcite spits out and generates is performant. So maybe a good question for, Stamatis or Jacques would be, assuming that I generate a bunch of, joins, right? Like an inner join or a left join, and those are nested. Will Calcite be able to pull that out into something like select, where the foreign key ID is in this array? Will it still be efficient? Or was there the potential for it to be, pretty slow?
I mean, if it's possible, I mean, you can, it doesn't matter how, if you describe, let's say, the plan with inner joins or nested things, and we can apply rules to a nest and do let's say, the join reordering optimization that Alex spoke at the beginning, it should work. So I would consider the n+1 problem another kind of thing that we have when we do, object to relational mapping, or I would think it's another level of complexity, like sending the multiple queries. But now it's not about sending multiple queries. You're going to have an operator tree, and then you have to put the operations in order. And I guess one point where you can kind of have the n+1 problem is if you have, like, let's say on the one side of the join, a subtree, and the join operation is a nested loop. If you have a nested loop, then it means that for every row on the left side, you'll have the whole subtree on the right re-executed, but it's just an implementation detail. And it's part of the query optimization. So, I mean, regarding the join operator, the optimizer can choose to do it via a nested loop join, via a hash join, via something else, via a merge join or whatever.
But whatever it chooses, it's probably going to be about as close to the most efficient theoretical query you could generate, right? Given those relational expressions, and that's part of the appeal.
I think the only caution I'd make there is there are definitely situations where you're better off not running one query, or at least I have definitely seen situations where that's the case. And as far as I know right now, that's not something that Calcite would do. So Calcite should do a good job at optimizing the one query reasonably well. I mean, you have to, there's certain kinds of patterns where maybe it wouldn't do as well. Like if you start decorrelating things before you convert it to, say, SQL on the bottom end, if you're running back to relational or something like that. But if you assume that one query is the most optimal way to run something, I think it'll probably do reasonably well. If it's a situation where actually the ideal is to run multiple queries, then I don't believe that there's any code in Calcite to do that, to decompose something into multiple separate trees that are sort of executed independently. You could build something on top of what Calcite has, but there's not something that I think exists there right now.
That makes sense. One last question that I have. Sorry for taking up so much time. This virtual joins or virtual foreign keys across schemas. Is that possible for me to join, say, user.id in a Calcite schema coming from Postgres, and to-do.userid maybe coming from a Calcite CSV file, just arbitrary virtual joins?
Yeah, I mean, in Calcite, tables are just tables. It doesn't matter where they're from, and so you can join across anything. Whether you can, so you can join across anything. It's not the constraints are not in Calcite. The constraints don't inform what's possible to join. They simply give you considerations when you're trying to decide statistically what makes sense to do. But you can join any two tables. Okay,
and I can put that rel constraint object, I assume, across any arbitrary two tables then. The one that comes from
if you just want to build joins, you don't need to use constraints at all.
Oh, okay. Got it.
Like constraints inform, I'm not even sure how much they inform it, but I think conceptually speaking, they have the opportunity to inform the metrics or statistics that the planner looks at. But generally speaking, I think like you probably don't need to get into constraints in the simple case.
Okay, thank you. I am going to change my strategy then, because I was going to use rel referential constraint, but I had no idea what it actually implied. Thank you.
Yeah, as far as I mean, if someone else wants to disagree, I don't want to. But in general, I think most joins you just build a join that has two sides to it and say this is the keys that the match.
Okay, sweet. Thank you.
And Gavin, I think the talk that Alexei gave is going to be helpful as you move along, because you might generate a lot of joins with a lot of tables. GraphQL queries can be quite big.
Yes, they can.